Dobrý den. Mluvím něco česky, ale bohužel to nestačí pro celou prezentaci. And that's why I'm going to continue in English. Sorry for that. Okay. Just like to introduce myself. My name is Ralph Hische. I've been working at NVIDIA for 4 years now. And I'm the business development manager responsible for the professional line of products, everything which has Tesla in its name, everything which has DGX in its name. And I cover the region of, well, basically Central and East Europe. And even the Czech Republic falls into my responsibility. I don't deal with all verticals. So I am actually responsible mainly for the higher ed and research customers. So all the universities, all the big data institutions, big science institutions like typically in Germany, the Max Planck, the Fraunhofer, the Helmholtz, and the Leibniz societies. I deal with all of them. Okay, this is how you can reach me. Best way to reach me, either my mobile phone or my email address. And I'd like you to remember one little promo code now. I've listed it down here. My personal VIP promo code, it's NV for NVIDIA, NV, then R Hische, the first letter of my first name and my whole surname. I'll ask you at the end of my presentation again, and I'll tell you what this is good for, because we have a very, very large event next week in Munich, and it may be of interest for you because Munich is not that far away from Prague. So, what I would like to talk to you about today, I can't cover all of the news of NVIDIA. The 2 hours aren't sufficient for that. I would be talking the whole day, probably. So I'll like to concentrate on a few things. What I will touch today is the topics, everything which is Tesla related. So Tesla is the premier product, the data center product for AI and scientific code acceleration. So our GPUs, which have been designed for doing specifically that, and we have one here. I'll pass it along. Everyone can touch it. Don't worry, you can't break it. It's already broken. This is the most complex the most complex chip and the most largest chip in the world. So we're actually approaching the limits of what's possible. These 800 square millimeters of silicon is the most complex you can get today. We've actually gone to the limit of what's technically possible. And it's almost 22 billion transistor functions in a single chip. 4 of these actually form the basis of this DGX station. Petter of M-Computer, in the presentation following mine, will do a hands-on demonstration of what's possible with the sheer processing power you have in this workstation and how you can utilize the readily available containers for doing your deep learning work. So it's Tesla. I'll be covering Volta. So basically the V100. I'll be covering the whole DGX line of products. So starting with the DGX station, 4 GPUs, the DGX1, 8 GPUs, and the largest thing we have available, the DGX2, 16 GPUs, which is top of the line, top-notch technology available today. Then I'll go further on into AI versus HPC. Why we are able to do both with one chip, and what actually each of these application fields requests of the accelerating power. There's typically differences in precision needed, et cetera, et cetera. Why did we introduce the TensorCourse, for example? I'll get into that a little bit. Then, because I saw that on the LinuxDays, you do a lot of embedded, a lot of robotics, and a lot of small embedded mainboards and using them for specific tasks. I'll take you through the details of our newest product, the Tegra embedded chip, the AGX platform, which we announced a few weeks ago. I think that's going to be the last presentation, and it's actually also the most recent information we have here. I'm not going to cover our consumer cards, so I'm not going to talk about 2080 or other products, and I'm not going to talk about Quattro. That would be topics for another presentation. To start everything, I'd like to show you a small, a short video to show you what we're actually doing actively with our AI customers worldwide. These are all real projects which are being done by our customers. So please enjoy. Oh, no sound?
I am a protector.
It worked 10 minutes ago. We actually tried it. I didn't change anything. I can go back again and start it again.
Protector.
Maybe I should close PowerPoint and start it up again, because I started PowerPoint when we pulled off the HDMI connector in between to test the workstation. This is Windows. Sorry about that. We're at a Linux day, not a Windows day, right? So let's try it again. Let's see what happens. There's no sound. This is bad.
I am a protector.
Let me pull off the HDMI again. I hate problems which sometimes work and sometimes don't.
Protector.
You have it in the stream, but we had both before. Yeah.
Exploring the expanses of space to keep our planet safe. all the species that call it home.
Okay, then I'll sing now, or I'll say something about it. Okay, what we see here. Okay, I'm a healer.
Giving doctors the vision to create amazing new cures.
What we see here are various applications in healthcare.
And using the heart's own magnetic field to diagnose itself.
Monitor.
I am a guardian, searching a mountain of data to keep us safe when we travel.
Seeing everything, object detection and tracing at airports.
And a
here,
sea of people
looking for specific
to find a
people.
lost
So
child.
what they're looking for here is a child who's lost himself in space. And they found him because he has this specific.
I am a helper, powering autonomous machines that simplify our
There are
lives.
a lot of robots helping us and replacing our jobs. And working 24 hours a day.
Capture our
This
greatest
is also
adventures.
So it's actually a flying drone which follows its user and records his activities.
And make us whole
An
again.
artificial hand. Learning how to play piano.
I am a visionary,
Self-driving cars. In Munich, you're going to see it.
enabling taxis that don't need steering
Over 20
wheels,
different vehicles, from cars up to trucks
and those that don't need roads.
Airbus. Flying taxis.
I am even the composer of the
And even
music
the
we're hearing. I am AI.
Okay. Well, we are actually in the third evolution phase of computing. So everything started in 1995 with the internet, of course. Then 2005, the mobile cloud. We're fully interconnected with our mobile phones, and the next step is going to be AI and the Internet of Things. So everything will basically be intelligent. Even the clothing you will be wearing will have RFID tags to transmit data, etc., etc. So it's going to go a long way. And imagine all the data coming from these devices. It has to be analyzed. You don't just want to sample this data and store it because that's useless. You have to analyze it in an intelligent way to do intelligent things with it. Let's come back to NVIDIA. NVIDIA actually started as a computer graphics company. Everyone knows what we started with, and we're still very proud that we're the leading company in computer graphics on PCs. That is actually the main aspect of our company. Still, we're still doing the majority of our revenue with standard computer graphic boards. But we're actually, in that sense, we don't produce the cards themselves. We're actually a chip supplier, and our OEMs actually manufacture them and bring them to the players. 10 years ago, we started with GPU computing. So 12 years ago. 12 years ago, we started with GPU computing. Scientists at that time realized that the massive parallel processing power of our GPUs can not only be used to calculate nice colors on the screen and nice pixels, but you could also use that to accelerate scientific codes. And that's when we introduced our first CUDA libraries, 12 years ago. And now, 6 years ago, we actually had the breakthrough of artificial intelligence, starting with the ImageNet competition and Alex Krizhevsky, who actually won the ImageNet competition by a large margin, being the first one to actually deploy GPUs. So that's basically our story behind it. For the first time ever, we can now not render
What's the story with all the elevators lately? I heard Kylo Ren destroyed the one over in D sector. If you ask me, who's ever in charge of this place should be transferred to Hoth. What?
For voltage. It's ray tracing, not rendering in real time. Actually, in former times, a rendering farm would calculate frame per frame. And each frame would basically need hours, days to generate. We're doing this at 60 frames per second. It's real-time ray tracing. It's the first time ever in history that ray
You think
tracing
she heard us?
in real time is...
Yeah, I think she heard us. At least we blend in for once.
Sorry that we can't hear what we're talking about, but you can listen to it in the live stream.
So let's take...
Okay. So what we actually see is that Moore's law is coming to an end. If you take the single-threaded performance of a GPU, you actually see that we're not adhering to Moore's law anymore. The advances of raw processing power from generation to generation of CPUs is not holding up to Moore's law. The only thing which goes above Moore's law at the moment is our GPUs. And our computing performance is growing better than Moore's law. And this is actually the reason why GPUs are being adapted more and more, not only in HPC, but definitely also in AI, where the need for massive parallel power is there. If we take a look at what happened between 2013 and 2018, if we take the old servers with Fermi, and this also demonstrates it's not only a question of the hardware. It is a question of the ecosystem around it, the whole ecosystem. So this includes everything from our cuBLAS, cuFFT, cuSPARS, all our mathematical libraries we supply, up to CUDA, up to other libraries like cuDNN, which is basically the one you would be needing for deep learning. And if we see the advances here, this is a massive speed up within 5 years in terms of hardware and the ecosystem around it. Everything is progressing as a single ecosystem.
What the numbers mean in the tables?
Here, these,
In the tables,
these numbers reflect the version numbers. Okay, so in 2013, for example, the cuBLAS version was 5.0, and now we're at 9.0. So those are the advances in the versioning of the libraries we supply. So the Tesla platform, I was talking about an ecosystem. The Tesla platform, of course, on the bottom side, you have the raw hardware, and that could be either Tesla GPUs, which I'm talking about today, virtual GPUs. We also virtualize our GPUs, so you can use that in virtualization installations, virtualizing whole desktops, virtualizing workstations. Of course, our DGX family, where you see one member here. The HGX systems, which is actually the inside of our DGX systems supplied to our partners, who then manufacture their own systems around it. And of course, it's also our OEM partners who integrate our GPUs in their servers. And on the top side, it's even the cloud suppliers who have GPU-accelerated instances in the cloud you can use. On top of that, we have our various libraries, and of course, our compilers, the most prominent one from PGI. PGI is a member of the NVIDIA group now, so we actually purchased a compiler maker. So that's why they work best, of course, with our GPUs, yes. And then it's, of course, in terms of applications and frameworks. Here we see a few of the AI frameworks. So the most prominent ones, Caffe2, PyTorch, TensorFlow, MXNet, and then the applications like Amber, LAMPS, NAMD, etc., GROMACS. I'll get into these applications and how many we support later on. And then on top of that, it's of course either content, content. For example, you address, if you use translate.google.com, you're actually using GPUs behind it. That's why it works so good. And of course, you also have enterprise applications in various fields of, so starting from healthcare, manufacturing, engineering, and then in terms of supercomputing, I'll go into the supercomputing side later on too. It's the most adapted platform for accelerating HPC. If we take a look at the raw numbers, these are the numbers of the CUDA library downloads we've been seeing. And so from 2012 to 2018, it's eight times as much. So we have 8 million downloads of our latest CUDA libraries already. The top 15 applications are accelerated out of the box. And we are #1 again, or we are part of the #1. So the fastest supercomputer of the world now is Oak Ridge National Laboratory's Summit computer. It has over 120 petaflops of LINPACK processing power, so FP64 double precision. And in terms of AI performance, so the reduced precision FP16 performance using our TensorCourse, it's 3 exaflops. This supercomputer has 3 exaflops of raw processing power. So we already have an exaflop computer in the sense of AI performance. It is the first exaflop computer worldwide. Then Japan and Europe's the fastest one, Pete Stained at CSCS in Lugano in Switzerland. I'll get into a few details on that later on too. Okay, let's skip that one. It's just repeating. Let's go into the Tesla platform. Just a few examples of how much we can accelerate. So reinventing the lithium-ion battery, for example. Everyone knew what problems we had with some mobile phone makers, with their phones catching fire and burning. They had to redesign their batteries, which they basically did. And they did this, of course, with the help of accelerated computing. The processing power needed for solving this problem was actually 3 million node hours in terms of normal nodes. These 3 million node hours were calculated in 7 days on the Titan HPC computer in the States, in Texas. Same thing here with climate simulation. The need would be 100 million node hours, and it was calculated in 840 days on the Pete Stained installation. And understanding HIV required normally 10 million node hours. That one was calculated in 16 days on Blue Waters. So you can see the massive speed up, which is possible if you can utilize the processing power of the GPUs. Okay, another few examples here. Schlumberger, they do oil and gas discovery. Everyone's looking for the last instances of oil and gas on this earth. There's not going to be much anymore, so they're investing a lot of money to get their hands on the last resources. And they've been seeing a 10 times increase in data processing. Or USPS, they actually use deep learning for solving the traveling salesman problem, actually streamlining the delivery routes of their various trucks to keep them to keep the delivery as fast as possible. Okay, then let's get down to the actual heart of these systems. So Volta is the basis of the fastest supercomputer. I mentioned that, so it's Summit. Summit has a FP64 performance of 122 petaflops, and as I already said, 3 exaflops of AI. They use 27,648 of these. Gets very hot in there. I wouldn't like to pay the electricity bill. But in terms of the processing power available, if you would install that with standard CPU-based servers, it'll be a lot larger and require a lot more power too. Okay, these are Oak Ridge National Laboratory, the fastest one. The second fastest one, also based on similar systems. These two systems actually don't use x86 processors. They're based on IBM. They're based on IBM power-based systems. And they're the fastest two in the world at the moment. Sierra is a little bit smaller than Summit, but it's still enough to keep it at second place. And the fastest one in Japan also uses GPUs, has 20 petaflops. Pitt-State, the fastest in Europe, uses over 5,000 GPUs, also 20 petaflops. And the fastest industrial installation also uses GPUs, and it's in Italy. It's from NE, and it achieves about 12 petaflops. That's the fastest industrial one, which we can mention. There may be others, but they don't want to be mentioned. Okay, I'll skip this one. Okay, so what we're actually looking at is using weak or using strong nodes. What we actually implement are strong nodes. This is also what is implemented in Sierra and Summit. We use very strong nodes. They have 8 or 6 GPUs per node, and they have a massive processing power per node. They do not have to leave the node to achieve a higher performance. If you use a lot of weak nodes, you have scaling problems because sometimes it does not scale. If you scale to 16 or 32 or 64 nodes, it may not scale linearly because you have a communication overhead and you have a weak communication. You have a weak communication, the fastest one being InfiniBand here, but it's still much weaker than doing it in local memory or doing it in a local device. If you have to leave your node to communicate with other nodes, you're going to have a communication overhead, and that will definitely, you'll hit a limit in scaling. You can add as many nodes as you like, but you're not getting more performance. And you're actually going to degrade sometime even. And the other thing is, you're spending a lot of money not on computing power. You're spending a lot of money on racks needed because you have more devices. You're spending a lot of money on network fabric you don't need if you have only a few fast and strong nodes. So you have a lot of overhead you're spending money on, and you're sacrificing the money you're spending on the actual processing power. 70% of the supercomputing workloads are already accelerated. Now we have here's a list of the top 15 HPC applications, and all of these are GPU accelerated out of the box. We have a list of supported applications, and this list has over 550 commercial and public domain codes which are accelerated out of the box. And of course, you can accelerate your own codes if you use the libraries and the compilers we provide. This is just an overview of the various fields of science. So if you take a look at the life sciences, we have over 50 applications accelerated there. Manufacturing, CAD, and CAE, it's over 111 applications, and so on and so on. In deep learning, we support almost every deep learning framework out there. So there is basically no popular deep learning framework which is not accelerated by our CUDA TNN library. Okay, what we see at the moment is we see a convergence of traditional HPC on the one hand and AI novel methods on the other hand. But the two have different, need different resources. In HPC, you're basically dealing with higher precision. So in HPC, you'll basically be using FP64 or at least FP32 single precision. We even have scientific codes which need quad precision, so FP128 if you go into coding and special algorithms in that sense. AI, on the other hand, tends to go into lower precision. So we're seeing in AI an adaptation of, normally it's FP32 you're using, so single precision. But there is a tendency to go to half precision, FP16, which only needs half the amount of memory for the neural nets, because you're only using FP16 values per neuron. And even going down to int8 or int4. We're seeing first adaptation of int4. So using 4 bits precision for inference purposes to have a fast inferencing. So it's quite different things. These two fields of application are requesting from the hardware they're running on. And the good thing is Volta meets both requirements, because we have both in one single chip. With our older technology, Pascal, we did have various different boards which were actually designed to meet a specific requirement. So we had the P4 and P40 boards, which were designed towards inference, and we had the P100, which were actually more designed towards training. So we differentiated between training and inference because those requirements were different. With Volta, we have a single chip, a single implementation which meets all requirements, regardless if it's training or if it's inference. It does everything at a perfect top level. Okay, I'll skip this one. Okay, let's get into TensorCourse. Volta, for the first time, introduced the concept of specific tensor cores. Pascal didn't have tensor cores. Volta has additional tensor cores, and with the Volta V100 chip, which is also at the heart of the system, each Volta chip has 640 dedicated tensor cores, which do a very specific operation in hardware. So what we actually did is we took a look at the common deep learning frameworks, and we analyzed what is the most common function they are performing. And it is this 4.4 matrix multiplication, which is actually the most common operation being done during training and also during inference. And so we said we're going to implement that in hardware and see that this operation is done in a single cycle. So what actually happens is that we have a specific hardware which does a 4.4 matrix multiplication with FP16 plus the addition of a FP16 or FP32 4.4 matrix and writes that into a resulting matrix all in one cycle without ever touching the memory of the GPU again. So there is no memory interaction. That's why it's done in a single cycle. It's hard-coded. And this is why we achieve 125 teraflops out of these 640 tensor cores within a Volta, which goes way beyond what we are capable of using our native FP16, FP32, and FP64 registers. Here's just a few examples of that. If we take a Titan node, and the Titan node doesn't use Volta, and we now take a single node of the Summit HPC installation, we see a 50 times speed up using a FP64 and FP32 mixed precision application. And we see a 150 times speed up if we use FP16 only. And FP16 only will use the TensorCourse, and this is why we have a much higher speed up here. We then analyzed, okay, if we not only take a single benchmark, if you take a single benchmark, of course, you could pick that benchmark which shows you the best result. That's marketing, and put up the highest value. What we did here is we took a typical mixed HPC workload. So we analyzed the workloads of our major HPC customers. And we just took a typical workload, which represents what they would basically be doing, and this workload is a mixture of various applications. So it's Amber, NAMD, Quantum Espresso, Spec FM 3D, etc. We applied this mixed benchmark on ZPU-only system, where we needed 160, and we achieved the same throughput. So the benchmark was, what do we need to achieve the same throughput as these 160 CPU servers? And we could do it with 8 accelerated servers with 4 V100 GPUs each. And we got the same throughput in terms of this mixed workload. But if you take a look at how much space do I need, how much energy do I need, and how much money do I need to buy it, you get these fascinating results. You get the same throughput at 1/5 of the cost. You get the same throughput at 1/7 of the space, because you're not using that many racks. And you get the same throughput with 1/7 of the power you invest into this system. And whoever sees these two slides doesn't have to think about what he purchases. This is very, very clear and fast forward. Let's take a look at the AI side of the picture. Some examples of our customers using AI and accelerating it with GPUs. After using GPUs, they achieved 60 times better latency for a typical application. What they actually do here is finding similar images. So it's image and object recognition they're doing here. iFlyTech actually does. This is the leading supplier in China. We don't have similar services here, but they have a different problem than we do. We're used to typing. We're used to typing words and typing messages because we have a very simple alphabet. The Chinese, they have problems entering their symbols using a keyboard. They basically have to combine various symbols to achieve what they would like to have. So they do it in a more natural sense. They use spoken words. So they use a speech to text translation service. So what they actually do is they talk to their mobile phones, and this service will analyze the spoken words and write them into the application in written form. So it's a speech-to-text transition application. And using GPUs, they were able to achieve 20% higher accuracy. Doesn't sound much, but going from 70 to 90% accuracy is a lot. And here's the same thing. Also, using GPUs, they achieved a much higher, major improvement in the user engagement. Healthcare, also same thing. Over 80% accuracy, analyzing medical images. 50% reduction in road repair costs. What's this? What they actually do here, they analyze in terms of image analysis, they analyze the roads, and they are able to detect a hole before the hole happens. So this is predictive maintenance. And this is being used by an American city already in productive use. And they are able to detect where the next hole will happen before it happens. And so they go out and they do planned maintenance of the road, planned construction sites before it actually happens, and it's unplanned and leads to massive traffic jams. And they do this with a very high accuracy. They're able to detect what happens where before it happens. And that's what deep learning is good for, and that's what neural nets are good for. I even know that companies like the SBB, so the Swiss Railways, they're also planning to use predictive maintenance. So they will exchange parts of their locomotives, exchange parts of their of the wagons they're using, exchange parts of the signaling and track system before it breaks. But don't exchange it too often, because that'll result in higher costs. So you have to wait for the right moment in time to exchange it in a planned manner, and that's the whole magic behind it. And this is actually what also GE is doing with their gas turbines here. This is also predictive maintenance, replacing parts before they break, but using them as long as you can before they break. What we see is these neural networks, the complexity of these neural networks is growing, and it's not growing linearly, it is exploding. So this is exponentially growing. Just a few examples, image. Here, Google, everything started with AlexNet. AlexNet back in 2012. That was that complex. It was not very complex. And GoogleNet, ResNet 50, Microsoft ResNet 50, and now we're at Inception version 4. This is 350 times complexer in terms of number of layers, in terms of neurons simulated, etc. So it's 350 times complexer. Even speech is growing vastly. If you take deep speech 2 and deep speech 3, you see it's 30 times complexer than it was 4 years ago. And the same thing applies to translation too. So we see the complexity is growing very fast, and it's growing more than linear, and it's growing more than Moore's law. To be able to cope with these very complex neural nets, you have to have the same increase in hardware acceleration too. If we take a look at the types of neural nets, being used, this is what we call the Cambrian explosion. Back in 2012, we had one neural net. Where is it? Okay, I can't see it, but it should be somewhere here. The AlexNet should be somewhere over here. We don't only have convolutional neural nets now. We have recurrent neural networks like LSTMs invented by Jürgen Schmidhuber and Sepp Hochreiter from the Munich University, for example. The latest addition in networks are GANs, generative adversarial networks. In GANs, you actually have two competing networks, one network doing something and the other network questioning what the first network is doing. A very prominent example of that would be you could train a network, for example, to paint like Leonardo, or to paint like another painter. You could train him on existing pictures, and this network would be able to learn the specifics of this painter. And again, the second network, which tried to prove that the first network is doing something fraud. The second network would try to prove that the first network is not Leonardo or is not this specific painter. And so these two networks actually learn from each other, and they are able to reach a level by pushing each other higher and higher in what they are doing. The first network would improve his skills. The second network would improve questioning that it's correct what he's doing. And so that's actually what happens in a GAN. Reinforcement learning, the same thing. And then we have new species, which are actually mixtures of various networks. You can combine them. You can actually do something like not only using a single instance of a neural net, but for example, using a group of experts, like we humans do too. If you ask a single doctor, he will give you a single opinion. If you ask 12 doctors with different opinions, you can then say, okay, democracy wins. If 7 of them tell me this, then it should be correct. You could simulate something like that in terms of neural nets too. So a ensemble of experts, for example, and competing networks giving a final decision. So there are actually two phases to everything. It's the training phase and it's the inferencing phase. In the training phase, the first thing you do, you design your neural net. That's one side of the story. Which neural net do you take? Which neural net fits to the problem I want to solve? We saw that there are a lot of neural nets. So this is what we need the experts for. The domain experts who basically did that 10 years ago in handwritten coding. And you then take this neural net you designed, which has no capabilities at all. It's dumb, like a newly born child. You then train it with tagged data. You train it with tagged data, and you then give it wisdom. It is trained, and it converges to a specific level of capability, and at that level, you then deploy it. For example, I drive a German car, and this car has a head-up display. And in the head-up display, it not only shows me the speed I'm traveling at, but it also shows me the traffic signs he has seen and detected. And so actually what you do is you train a neural net with basically something based on AlexNet, because it's image and object recognition. And you train it on German traffic signs, for example. And it then reaches at some time, if you train it with millions and billions of German traffic signs in all weather conditions, you'll get really good at detecting these traffic signs. You then take this readily trained network and you deploy it in the sense that you put it into a car. It runs on a kind of hardware there. And in these inference phase, the amount of processing power you need is basically much lower than in the training phase. In the training phase, you'd need about 100 times the power to train than the inferencing phase. The inferencing phase is much easier because then it's only fast forward. You just have to go through the network in one direction and get to your output. In the training phase, it's going through, seeing if you have the right decision, backtracking again, and, well, doing modifications to the path you're backtracking. In the inferencing phase, this is not the case. Okay, we've had this content already. We support all major frameworks, and what results in this massive speed up is that we have the TensorCourse, we have the NBLink, which is the high-performance interconnect. This is also one of the distinctive factors of our professional line of products. We have a dedicated high-speed NVLink. Normally, if you do a multi-GPU setup and you're using PCI Express-based boards, they would communicate via PCI Express. But PCI Express is very limited in terms of latency and in terms of bandwidth. PCI Express basically gives you, well, in a realistic sense, it's around about 10 gigabyte per second you're talking about. With NVLink, we have 25 gigabyte per second on a single link. But in Volta, we have 6 of these. So unidirectionally, it's 150 gigabyte per second we have within a communication bandwidth. And it's even 300 gigabyte bidirectionally. So that is vastly more than what you could achieve with PCI Express. And then we have NV switch, but I'll get into those details when I talk about the DGX2. Okay, this is the TensorCore, the V100 GPU we're talking about. We have 5,120 normal CUDA cores within it. It's 640 of these Tensor cores I've been talking about. In terms of performance, we're talking about 7.8 teraflops LinPack performance, so double precision performance. It's 15.7, twice the amount in FP32 performance. And normally with FP16, like in Pascal, we would have, again, double that amount in FP16 if we would use the native FP16 registers within it. But using the new Tensor cores, we achieve 125 tensor flops. So that is a massive increase. So that is basically somewhere between 6 to 10 times speed up versus a mixed FP16, FP32 setup. We have 32 gigs of local memory, and it's HBM2 memory with a bandwidth of almost one terabyte per second. This is also a differentiating factor between the professional line of products and our consumer boards. The consumer boards use, the older ones use GDDR5. The newest ones, the RTX range we just introduced, the RTX 2080, that one uses GDDR6. The difference is about factor 2. So GDDR6 has about 500 gigabyte per second versus the 900 gigabyte per second we have with the HBM2. And of course, we have the 300 gigabyte per second NBLink connectivity we have implemented here with the 6 NVLink connections available. By the way, the DGX station uses the NBLink also. This is not implemented. These are basically PCI Express-based boards, but the communication is with NVLink is done over a special connector, which is on the top of the boards. If we take, for example, the relative time we need to train ResNet 50 on a dual CPU setup, that would require 25 days. On a single Pascal node, it would take 4.8 days, so 1/5 of the time. On a single Volta V100, it's 30 hours. On a DGX1 using 8 of these Volta, it's 4 hours. And if we take 8 of these DGX1s and scale that, then we're finished in 14 minutes. So we see that there is scalability also. This is the Tesla HGX2. This is not the DGX2. The DGX2 is our own product, but we supply the inner system of the DGX2. We supply that as HGX2 to our OEMs. They are able to design systems around it. There are no HGX2 systems available yet. We do know that the major cloud providers, I don't want to name them at the moment, but everyone knows who I'm talking about with these massive computing centers worldwide. They also implement their own systems. So they design their own systems, they manufacture their own systems and use them in their computing centers. But the inner world is the same. So this is actually what the DGX2 looks like internally. It's 2 layers with 8 GPUs each and interconnected by a high-speed NV switch technology.
It's for you, form factor?
10U. The DGX2 needs 10 rack units. And weighs about 180 kilos. So you can't transport it with 2 people. We actually at installation we tell our partners that they require a special lift to place that system into the rack. and it needs 10 kilowatts. But it has 2 petaflops of processing power in terms of AI, 2 petaflops within a single node. Yeah. So this is actually the NV switch. In the DGX workstation, we use the 6 links, the 6 individual links we have to connect to the other partnering GPUs, but always using a single link. So using a single link gives you, as I said, 25 gigabyte per second or 50 gigabyte per second bidirectional. And because we only have 6 links, this GPU can actually only talk to 6 other GPUs if it would be able to communicate directly. If you have more than 6 GPUs, like we have in an 8 GPU setup, what do you do then? You do not have enough links. So in that case, you would do a kind of hypercube constellation where not every GPU is able to talk to the other GPU directly, but may have to go one hop over another GPU, which gives you, of course, latency. And you're always limited because you're only using a single link. Going to 16 GPUs within a single system even makes it worse. So when we designed the DGX2, we said we have to do it in a different way. So what we actually did then is, like you have a PCI Express switch chip, we designed something which calls itself NV switch chip. What this NV switch chip does, it switches NV links. So what we actually do then, with all combined 6 links, we go to the switch chip. So it's like a direct link with 300 gigabyte per second, a direct link. And because we have a fully switched and it is non-blocking, this architecture is non-blocking, it's fully switched, every one of the 16 GPUs can talk to every one of the other GPUs directly at full bandwidth of all combined links. So it's talking 300 gigabyte per second with another GPU, and you can have 8 of these 300 gigabyte per second communications happening at the same time without anything blocking. And this is the massive speed up within a DGX2. This is actually the novel feature within a DGX2. We're now talking peer-to-peer at full bandwidth, at full combined bandwidth. And this is the main differentiating factor between a DGX2 and a DGX1. It's not only going from 8 to 16 GPUs, which would give you double the performance. It's also, we have an internal massive increase in bandwidth, which is unseen before. And we're seeing 10 times increase in codes using this internal bandwidth. So if you have a code or a problem which is running at, and it has a lot of communication happening at runtime, like in FFT, for example, there's a lot of communication going on. There's more communication than computing. Then that code will benefit very much from the improved and increased internal bandwidth. And that's why we're seeing, although we only have twice the amount of GPUs, we're seeing an increase of 10 times in performance, because the bandwidth was the limiting factor before. No, we don't have NBLink in RTX cards. Okay, so I can go into this question. Of course, we are often asked, why do I need the professional cards? Can't I do it with the consumer cards? Yes, you can, and we encourage you to do it. Because if you have a limited budget and you want to get the most out of your limited budget, and you're not using the benefits of the professional boards, which is multi-GPU, multi-node setups, if you're limiting your problem to a single GPU instance, go ahead, use them. We're glad that you're using it and getting acquainted with CUDA and everything and so on. But if you want to go the next step, if you want to take the next major leap, then you're going to go massive GPU, you're going to go multi-GPU, you're going to go multi-node, and that's when you're going to have to ditch your consumer GPUs and take the professional ones, because they have features the consumer GPUs don't have. And that's scalability. Scalability, availability, the memory performance you have, the reliability, 24/7, and so on. That's the advantages you have with those. And also, of course, the support from NVIDIA in terms of containers you're using, in terms of optimization of the deep learning frameworks like TensorFlow, etc., to our GPUs. You only get support from NVIDIA if you're using the professional line of products, of course. Here's one of these examples. Just think of it as DGX1 versus DGX2. The DGX1 using 8 GPUs and the individual links. The DGX2 using 16 GPUs and the massive increase in internal bandwidth. And if we trained FairSec on it. FairSec is a language translation network. And this is a version which translates English into French. And on a DGX1, it took 15 days. On a DGX2, it only took 1.5 days, which is a speed up of 10 times, although we only have 2 times the amount of GPUs. Here we see the non-linear, so the much more than linear speed up due to the very high internal bandwidth we have. May I ask what's the time scale at the moment? Okay, that I'm in the middle. Then it fits perfectly. Yeah. Okay, we even did tests then. You could think, well, instead of taking a DGX2, I'll take 2 DGX1 nodes and I have the same amount of GPUs. I just connect them with the InfiniBand we supply on the system, and it should work then. We compared that, a single DGX2 versus 2 DGX1. And in terms of the a few benchmarks, we always saw that the DGX2 was at least 2 times faster, because we did not have this external link needed between the nodes. We were keeping within our very powerful single node and not having to communicate with a second node, although we're using EDR in InfiniBand at 100 gigabit per second, which is not slow. This seems to be the bottleneck. And then the internal bandwidth of a DGX1 is much lower, because we're only using individual links and not the combined power of all links at one time. And you see, it's not only one benchmark. Using four different benchmarks, we see the same result, at least a 2 times speed up. So if your problem size is large enough, then go for a single large node instead of 2 smaller ones. If your problem size is too small, you won't see this. Okay, yes. It's always a question of how big are your data sets, how large are your neural nets, how complex are they, how many layers do you have, etc. If you reach a specific level of complexity, or your data set reaches a specific level of size, then you'll be seeing these effects. Comparing a DGX2 with normal CPU-based servers, these are the results we saw there. In terms of AI training, a single DGX2 replaces 300 dual-socket CPU nodes, 300. And in terms of HPC, here the workload is a particle physics application. It's still at 60 times. So a DGX2 replaces 60 nodes. The replacement factor is not as large as in the AI training. We see the most increase in AI training at the moment. But even the HPC world benefits from this, and replacing 60 individual dual socket nodes with a single system will save you a lot of money. As our CEO Jensen would say, the more you buy, the more you save. Okay, let's get into what's on top of this hardware. What we actually provide is, if you purchase a DGX system, you also purchase service with it. And this service not only comprises of, we will replace your hardware if it's broken, we will send you replacement parts if something breaks. No, it's access to everything we have developed for these systems. And the foremost feature is you will have access to our enterprise portal where you can download all the Docker images we've prepared for you. So you'll find a TensorFlow Docker image there. You'll find a Caffe2 Docker image there. For every deep learning framework, for a growing number of HPC applications, I think it's already 12 or 15 applications where we already offer them. And for visualization too, we are offering the first containers for visualizing large data sets. You just grab these containers and you're up and running, and I think Petter will show how that works later on, how easy it is. You actually unpack the machine, you hook it up to the internet, and you're up and running within 15 minutes, basically. You don't have to install a single piece of software. I've had customers approaching me and saying, I can do that myself. What you're doing, I can do that myself. Give me a few Tesla boards, I'll set up a server, I'll do that. We did that. We supplied him the access to our benchmarking center in the US, and he started working on it. He started installing. To install TensorFlow, you have to install not only TensorFlow, but there's a lot of libraries and dependencies you have to install. I think it's around about 12 to 13 packages you have to install, and there are a lot of dependencies on it. You have to read about 400 pages of documentation if you're starting for the first time. A normal administrator gets the TensorFlow environment up and running in, let's say, 1 to 2 weeks. 1 to 2 weeks, it'll be up and running. But when the next major version change happens, he's going to start over again. And he's going to have to do all the testing again. He's going to have to check if the new version works together with these depending libraries or not, and so on. So he's going to have to be testing and testing and testing. Basically, he's going to have to need two systems. One for productive use, he's not going to touch until he's proven that the next version works. And he has to prove the next version on a system which is not productive. So you'll basically need two systems. We have an update cycle of the leading containers of 1 month, and the not so popular containers 3 months. So we keep very much up to track, and we work very closely together with all those development groups responsible for TensorFlow or whatever. We have direct contacts. They supply us with the alphas and betas before it even goes out. We already have the possibility of checking that in interaction with our systems. And you get all this for free. To come back to the story, he got the resources, he started testing. It took him 3 weeks to get the system up and running that it didn't crash. Before that, he said, well, I was tweaking here and there and doing a bit of fine-tuning here and there, but the benchmarks were crashing, they were not running through. He eventually got it up and running. He did then benchmarking on it, and he came back to us. He was convinced that he had very, very good benchmark values. They said, this is what I achieved. Good, aren't they? Then we compared it with our out-of-the-box containers. They were not very good. So basically, the bottom line is he invested a lot of work. He did a lot of things he as scientist should not do. He should invest his efforts in developing world-breaking and leading-edge research, and not administering a system and installing something. This is not what he's supposed to do. Leave that up to us. We'll get that up and running. You just grab that container, and you're perfect. That's actually what it's about. And we're actually, for the complete service, we're asking around about 7 to 8% of the hardware cost per year, which is not much. You pay more if you bring your car in, to service and have it serviced. You're going to pay more than that. Okay. On top of that, this is what the container depicts here. We also give you the possibility of attaching to our cloud. We have an NGC cloud where you can use cloud resources in the same way you would use the containers here. So you could actually do development on your local workstation, take what you've done in that container, place it into the NGC cloud, and use a massive amount of processing power in the cloud. So you can scale without having to start over again. You use what you've done locally, and these containers are exactly the same. You would import into the NGC cloud and have it run there. And on top of that, for orchestrating everything, we use Kubernetes. With Kubernetes, you could, for example, use a sort of failover system. If one system during training fails, it will take other resources and use them. Or if you'd like to scale, if you see that it's not training fast enough, you just use twice or 4 times the amount of nodes, and Kubernetes will scale that workload on the higher number of nodes then. So we support Kubernetes on that. And Kubernetes would be also the management feature, which would give you the access to the cloud resources, the EC2 cloud, Azure cloud, or other clouds. Mm-hmm.
Yeah, I have a question regarding the Kubernetes, because I know that in the past there was only one option to share one GPU per one container in Kubernetes. So I would like to ask if there is any support to share one GPU per multiple containers in Kubernetes. Because I know that with Docker there is no problem to share one GPU across multiple containers with Kubernetes.
I'm not in that detail of the Kubernetes side. If you come to Munich next week, the experts from the US will be there. Or if you're not able to come, send me an email. I can forward that question to our experts. They'll be able to give you an answer on if that's possible or not. I don't have an answer to that now. Okay. Okay, that was training. Now we're coming to inferencing. We saw that the inferencing data is exploding in the same way the complexity of the networks is exploding. So we have exploding features on both sides, on the training side and on the inference side. But it is vice versa. If you have more inferencing data, you have to analyze, and you want a higher precision of what you're doing. You, of course, have to increase the complexity on the neural network description size and on the training side, of course. Yeah. If we just have just hear a few examples of what we see in terms of inferencing data. It's 1 billion videos watched every day on Facebook. 1 billion. 1 billion voice searches per day using Google or Bing. 1 billion each day, or 1 trillion ads and rankings per day. That's the amount of data we're talking about. And if we go a step further, every single item is going to be sending data. It's not going to be 1 trillion. We're going to go to the next levels. Just add a few zeros to it, and you know what we're talking about. Just like to highlight one thing here, advertising. SAP, for example. If you invest in advertising, for example, you are Milka, and you would like to see how often was your advertising seen in the transmission of the sports event. you pay for the area you have on this starting gate, for example. You pay for advertising area down in the end zone of the event, for example. You pay for example, here. You pay for this area. You pay for an area on a Formula 1 car. But are you getting what you are paying for, is the question. Is the camera actually transmitting what it should be transmitting in your sense or not? What SAP does here, they do a real-time analysis of how often was your advertising seen during this live event, and you don't have to do any analysis, multi-day analysis after that. After the event is over, after the live event is over, you're going to have a fully analyzed picture of what happens. You will see how much of the time were you visible, how large was the area in terms of total space displayed, and you're going to have that analysis right at the second the live event ends. And they do this with deep learning. And then you can say, you can actually go to the company transmitting this event and say, hey, we paid too much, or if you were visible more than you paid for, you're not going to say anything, of course, yeah. But you can analyze exactly in real time what's happening. These are very, very interesting business cases, of course. Are you getting what you're paying for or not? TensorRT. TensorRT is a software product from NVIDIA. What TensorRT does actually is, it is a sort of compiler. What TensorRT does is, it takes a TensorFlow network or a TensorFlow application, and it tries to reduce precision where possible. So if you, in one layer, for example, could reduce from FP32 to FP16, it will do that. It's a sort of compiler, like the Java language. You could also compile and get it faster. This is actually what TensorRT does. And it makes massive use of the TensorCourse where possible, and will speed up the inferencing part. You can inference either by using the TensorFlow environment as provided and have that running in that, or you can do it with a specialized pre-compiled version which runs much faster. And we're talking about 10 to 20 times speed up, which will give you a performance improvement if you only have a limited processing power at the edge. For example, if you have a camera which analyzes a video stream. For example, you're overlooking a city square. You're monitoring a city square. You're monitoring an airport. You're monitoring a train station, Nadrashi somewhere. Then, of course, you would want to pre-analyze the data and not send that raw data to the computing center, because then you're going to have a huge overhead on transmission. You only have a limited processing power, so you have to get the most out of it. And that's where TensorRT basically comes into use. You pre-compile it, and it's much faster. And this is where we also have our newest product. It's the T4. The T4 is a reduced power consumption version of Volta. It's based on Volta. No, sorry, it's not based on Volta. It is based on the next version, the same version as on Turing. It's based on Turing because it has the reduced int8 and int4 capabilities. But everything within 70 watts. So you can use this within a server in your computing center without having to apply an external power supply, because it only needs the power supply which it receives via the PCI Express slot. But that is limited to maximum 70. And I think we also have settings for 60 or 50 watts if your server does not support the full 70 watts on the PCI Express. So this is the Tesla T4. 320 Turing tensor cores. Remember, V100 had 640, so it's half the amount, but it's Turing and not Volta cores. We have 2,560 CUDA cores. V100 has 5,180, so it's half the amount of Turing cores. You could basically think of the T4 as half of a V100, but it only needs 70 watts. This thing needs 300 watts. We have the at 300 watts, you're getting the most performance out of this V100 chip, but it's not the power efficiency point of operation. We have a power efficiency setting for the V100, so we've seen that if we reduce the power from 300 to 150 watts, so we cap at 150 watts power consumption, that will limit the frequency with which the cores will operate. At half the power consumption, we're still receiving 70 to 80% of the processing power. We're not receiving the top power anymore, but in terms of power efficiency, that's the sweet spot. 150 watts is the sweet spot. And if you take 150 watts, which is the power efficiency sweet spot, and you cut that V100 in half, you would be 70 watts. That is basically what the Tesla T4 is. With the single difference, we're using the tensor cores instead of the we're using the Turing cores instead of the Volta cores, Volta tensor cores, and it's only 16 gigabyte, and it's not HBM2, but it's GDDR6 memory we're using here. So that's the difference there. And you don't have any NVLink, of course. So if we take a look at the tensor cores and how they have evolved from Pascal to Turing. In terms of Pascal, we didn't have any tensor cores. So what is actually depicted here is a FP16 register doing operation. When we invented the tensor cores and we implemented them for the first time, and we used them in FP16, we actually got 8 times the throughput because we were doing 4.4 matrix operations instead of using individual registers, which would give you this amount of calculation power. If you then go from FP16 to int8, you reduce by a factor of 2. You get double the throughput, of course, because you're able to process the same amount of bits, basically, but the representation is only half that, so you get double the throughput of int8, of course, using the same hardware. And if you go down to int4, this is what the Turing tensor cores have, what the Volta tensor cores don't have. The Volta tensor cores don't have int4. So basically, the Turing tensor cores have shifted down one precision level versus the Volta tensor cores. But in terms of int4, you're going to get 32 times that throughput versus the old Pascal architecture, and that's where the power comes from at the moment. Okay, I'll skip this one. I think we've had ResNet and so on already a few times. Just an overview here. These are the frameworks on the one side we support, or a number of the frameworks we support. If you feed them into TensorCore, and it's not only TensorFlow representations, network representations. You can accelerate by running it through TensorRT. It's basically every network which supports the standardized Onyx representation format. You can output from another framework. You can output in the standard Onyx format, take that Onyx representation, run it through TensorCore, through TensorRT, and then deploy it on the hardware of choice. Now, what do you run that compiled network on? You can run it on, as we already saw, the Tesla P4, which is the old Pascal-based version, or the new T4. You can run it on Drive Peaks 2, which is the line of products we use for automotive, in our automotive sense. There are a lot of interfaces which are very automotive specific. CAN bus, for example, camera input and output. This module supports 12 cameras, so the next cars will have 12 cameras or more. Well, if they're going to be autonomous driving, they're going to have a 360-degree of vision, so you need a little bit more than 2 cameras. You can run it, of course, in your computing center on a standard Tesla V100. You can run it on Jetson, for example, and that, I think, is the best time to get into the Jetson. I'm going to go to the 8AGX presentation, which is the latest and greatest embedded platform we've announced. Just switch the... There it is. Oh, is this slow? Okay, we just recently announced Jetson AGX Xavier for autonomous machines. And what's behind that, I'll just tell you that in a second. Okay, to start with, we're talking about a single architecture in every sense. So this is a single architecture which is common amongst all our products, regardless if it's a normal standard graphics board, a product of our professional line of products, Tesla or our DGX, or our Drive Peaks line of products, or our Jetson embedded line of products. All of them share a common architecture. So what you can basically do is you can develop on this and deploy on this. It is the same architecture. We do not have different architectures. It's the same architecture throughout. Jetson is growing. I think this is a marketing slide, and you'll. I don't have to prove it. Okay, we have a growing community of developers, and more and more companies are using it. Okay, over 1 million units sold. That's a good one. Okay, we again don't have any sound, but just a few examples of what Jetson is being used for. Here is a monitoring of what's going on a construction site. This is autonomous harvesting. You don't have to pick your strawberries anymore. These robots are doing it for you. This is agriculture. This will reduce the amount of pesticides applying by 8 million. It's only applied on Now you know why the Chinese were so interested in the German company CUDA. We don't go shopping anymore. We only receive parcels at home. Postman says that he's delivering more parcels than others. He sends letters out. Okay, we've seen out there are in all various regions of application, there are billions of autonomous machines possible out there. So the market is huge. We have to address it. This is actually what this delivery tracked vehicle does. And the processing power necessary for doing these calculations and reaching these decisions is round about 20 TOPS. It's 20 teraops of deep learning power, inferencing deep learning power needed to have this thing react in real time. That is the processing power requirement. In an autonomous driving car, that processing power requirement is much larger. We're talking about a factor of 20 or 30 larger than this thing. But we have Drive Peaks products which address that. We're talking about the Tegra system. And so to power such a small system, it's 20 TOPS we need. Or video analytics, 30 TOPS required for doing this operation. A few other examples, aerial inspection. So we've seen that it's always somewhere between 20 and 30 TOPS needed in inferencing power to be able to construct these systems. And this is why we introduced AGX, Xavier. What we have here is 3 different performance levels. So you can actually deploy it in 10, 15, or 30 watt power consumption ranges. You can limit it. If you only have limited battery power, for example, you're inventing a drone, you may want to limit it to maximize the flying time of that drone, for example. Or you do not need the full processing power of 30 TOPS, which this platform provides. Then you can, of course, limit the power, scale down the processing power to meet your requirements. It's based on 512 Volta CUDA cores within this system, and it's an 8-core GPU, ARM-based GPU we supply with this system. So it is a system on a chip consisting of a 8-core CPU and a 512-core Volta GPU attached directly to it. And it delivers 32 deep learning TOPS. So it's actually 32 teraops of processing power in FP16. This is what this small form factor module is capable of. If we compare it to the previous version, so the previous latest version we had was a Jetson TX2. The Jetson TX2 was based on Pascal architecture and didn't have any TensorCourse, for example. And it was based on 256 cores Pascal architecture. We now have twice the amount of cores, and it's Volta-based. We have the deep learning accelerators. Pascal, we didn't have any. Here we have 2 of these NVIDIA DLAs, which is basically the Tensor Core. We also have specialized vision accelerators. We have higher performance CPUs. It's not the old Denver and standard ARM specified CPUs we now have. It's 8 cores of our new Carmel implementation. Memory is double the size, and it also has a higher bandwidth because we're connecting it with double the amount of bits. Storage is the same. Video encoding is much better. And we have up to 8 cameras instead of 6 cameras, which can be connected to the system. And that's about it. It's double the size of a TX2, but it's a much higher performance, of course. If we take a few benchmarks, and we'll again see the highest acceleration factor in deep learning. in deep learning, because we have these specialized deep learning accelerators now on our board, you'll see a speed up of 24. It's a speed up of 24 versus the Jetson TX2. That's the highest performance you'll be seeing from one generation to the next. 24 times the performance. That's not bad. And even in terms of CUDA, standard CUDA acceleration, we're seeing a speed up of 8. In terms of CPU speed up, it's twice the processing power. We only have 2 cores more than we did before that, but the cores are much more efficient, and so that's why we're seeing a double the performance from this new generation. The memory has more than 2 times the bandwidth, but that's due to it now being 256-bit instead of 128-bit. And if we take a look at the codec performance, it's 4 times. Those are the basic speed ups you'll be seeing from one generation to the next. If we compare this small form factor 30-watt implementation to a standard PC performance, and we're comparing it here with a Core i7 with a standard GTX 1070 GPU within it, we're seeing a higher performance in terms of AI inference on this embedded mainboard versus a standard PC with, well, that graphics card is not that small. It has much more cores than the implementation on the HGX Xavier. And the efficiency, of course, because we're using a lot less energy, the efficiency is, of course, much higher. So in terms of power, in terms of performance, we're a little bit better than the PC we're comparing it with, but the efficiency is, of course, factors beyond. This prototype used exactly this, needed over 200 watts versus the 10, 20, or 30 watts of our system. Provided 28 tops, we're at 32 tops, needs a lot more space, etc. We can now replace that with our single embedded board, and it does the same. So swap it out. That's what you use it for. Okay, we of course not only have a piece of hardware, we have a whole ecosystem around it again. We have the underlying hardware. It's a Jetpack SDK below that, and then we have a Isaac SDK used for robotics, where you can also do to train your robot, you can actually train the physical representation, the physical form of the robot, or you can do a vertical representation of your robot and train it in a vertical environment, in a virtual environment, which is actually what we did. We are able to simulate or emulate the physical robot with a virtual representation of it and train that in a virtual world. We, for example, trained a robot to learn how to play ice hockey. I know the Czech love ice hockey. They have good ice hockey players. Actually, it was a neural net which was trained, but we didn't provide him with the rules of ice hockey. So what actually, this robot, it was a tracked robot which had 2 arms and a sort of human head. It was placed on this ice playing field. It had the ice hockey stick, it had the puck, and of course it had the goal. We didn't tell him how to play ice hockey. He had to find it out by himself. He was rewarded if he did the real thing. So the first reward was if he hit the puck with the ice hockey stick, that gave a small award. If he was able to shove that puck into the goal, that was the highest reward he would get. We didn't tell them how to hold that stick. We didn't tell them how to hit the puck, etc. We didn't tell them anything. What we did then, we took this virtual implementation of the physical robot, and we made 1,000 copies of it. And we had them train within this virtual environment, had them train against each other and see which one developed the farthest. So he started holding it. He learned how to hold that stick. Okay, then he tried to hit the puck. He hit it with the wrong end, of course. He didn't use that end. He used the hand end, which is not very efficient. And after we were training that for dozens of epochs, we took a look at which of these implementations had the highest score. Which one learned the most? By doing, and it was reinforcement training, actually. It was reinforcement training. He taught the rules himself by using these rewards he was achieving. We took the best one, and we duplicated that one again, 1,000 times. And we had them compete against each other. After a few epochs again, we took the one which learned the best. And it didn't take very long until we had a perfect playing ice hockey player. And then you take that representation and you feed it back into the physical robot and you switch him on and he's playing. He's playing perfect ice hockey. But you can do it much faster and you can speed it up. And the same thing applies to autonomous driving vehicles too. All the major car manufacturers, I always see them when I drive down to Munich. I see a lot of Audis and BMWs driving on the autobahns autonomously. You see the drivers hands off and just watching. They are driving millions of kilometers. And they are processing video streams, a lot of them. But they are not sufficient for doing the training. We need about 10,000 times that data to be able to train a network which will efficiently drive in autonomous driving vehicles. So the question is, how do I do that? There are two ways of doing it. Either instead of using 100 experimental cars, I use 10,000 experimental cars, which is not very efficient. So the other way would be use the physical cars as one source of data, and for the remaining 80 or 90%, which I'm missing, use virtual implementations. And we're not only good at deep learning, we're also very good at ray tracing and rendering environments which look real world like. So what we actually think will happen, and it is happening, I know that because we're talking with all these major manufacturers, they're going to have cars driving in a virtual environment where they can also depict conditions you cannot do in a real world. It's like the pilots in a flight simulator. You can have them crash and nothing happens. Okay, you can simulate situations you cannot do in a real world because it'll be fatal. And so we really think that 80% of that training will be done in a virtual environment. So our GPUs will be rendering the environment needed, and the GPUs and the other GPUs will be training the networks on it. So those guys are going to need twice the amount of GPUs. That's a good part of the story for us.
There is one interesting thing because you can have actually different time in the virtual, which you mentioned. Maybe time may be running much more fast.
That is correct. Very good. I forgot about that feature. It's not only 10 that you're using 1,000 copies, but you're running it at 10 or 20 times the real time, because you can do that because you have the processing power for it. Right, very good. Mm-hmm. Okay. This is going into detail in the deep streaming. How many minutes do I have?
15.
Okay, then I'll see that I gradually come to an end. Okay, these are just a few examples of what this video inferencing system sees and depicts. And able not only to depict where the object is, but what type of object it is. So you can also do the classifying of it. Okay, we have a special Jetson developer site. Everyone who's interested in implementing on this embedded hardware will have will receive access to this developer site. We have specialized forums for it, etc. So you'll interact with all those Jetson developers out there in the world. The Xavier module. These are the prices which the modules will cost. Depends on the quantity, of course. And if you're using 10,000s, come to us. We'll talk about the pricing again. But for a first idea of what am I paying for this system, that's the amount which you will have to invest. That's coming soon. What's available now is the developer kit. This developer kit has a retail price of $2,499 and there is a developer special price, which is half the price. So if you become a developer, you can basically purchase one of these developer versions. And at our next event, at our GTC event in Munich next week, we will have a limited number at one of our partners' booths, and they will be selling them on site. So come with enough money and you can take one home. Okay, that would be it in terms of of our newest Jetson. Any questions on the Jetson before I continue on the DGX side? Yeah?
How is the Jetson connected with some, let's say, computer? If I make some analysis, how is the Jetson connected with some computer? For example, if I make encoding or some analysis, how to give the data outside the
basically, of course, you have your full set of networking capability, wired network, wireless network, that's all available on the module. If you want to use, it is the same thing with the TX2. We would supply the naked module. The naked module is a specific format and has connections on the bottom side. And that's basically what you would be using because you would, for your application, design a plug-in board for this module. The module is a processing unit itself. But you have to connect it to a sort of interface board which gives you the connectivity to the outside world you need. Yep.
Is it COM, computer on module form factor, or something else?
This form factor is our own form factor. We defined this form factor. If you purchase the developer version, you will receive a sort of standardized developer main board where this module is plugged in, and this developer board will give you the basic connectors to the outside world, whatever connectors you need. There's a full set, but normally you don't need all the connectors. You would limit it to basically only the connectors you need, or add additional versions if you're using some kind of industrial bus system or whatever. Yeah. Okay, then I'd like to show a few slides to DGX and our event next week. Okay, here again, the overview of the Tensor Core. In this slide, you'll see a little bit more information on what this Tensor Core does. And the magic is in this formula. So what actually happens here, it's 4.4 matrix multiplication you're using. That's why we have 4.4 elements here. This is matrix A, this is matrix B. And what actually is done in terms of mathematical calculation is matrix A with FP16 representation, so it's 16 elements of FP16, times matrix B, also 16 elements of FP16. This multiplication is done, and then a third matrix, a matrix C, which can be either FP16 or FP32. It can be mixed precision. And that is then written into a result matrix D, and this whole operation is done in a single cycle. No memory swapping here and here, back and forth. There's no access to memory, which would limit the capability of doing that in a single cycle. It is hard-coded, and this flow of operation is in a single cycle. And that's a massive speed up. This is a massive speed up we get from the Tensor Cores. And that's why it's optimized. We even see these Tensor Cores are actually used for deep learning. They accelerate all the deep learning frameworks out there. So every deep learning framework using our CUDA DNN will have access to this to these Tensor Cores automatically if they're using the newest CUDA DNN version. We've also seen scientists working on, hey, how can we use this massive processing power for HPC? And there's a few white papers for anyone who's interested in that. I can send those white papers. They're from Oak Ridge National Laboratory. They're from Jack Dongara, which is very known in the mathematical world, and it's from a Stockholm University. And they said, hey, if we need FP64 precision, why don't we use a multi-pass approach using the Tensor Cores? We can refine the precision by doing a multi-pass approach. As they said, let us use these 128 teraops we have at our disposition and emulate FP64 with it. And they were able to get 28 teraflops of LINPACK power, FP64 LINPACK power, out of the single Volta GPU, 28 teraflops. Remember, the FP64 performance of this thing was 7-something teraflops. So either you use the native 7-something teraflops with the native FP64 registers, or you get 28 teraflops, which is 4 times the power, using a multi-pass approach and other mathematical libraries. So there are ways of tapping onto these 128 teraops you have with the 640 additional Tensor Cores and using it for normal calculations. And there are a lot of groups, research groups, working on exactly deploying this in their codes. We have an own installation, and it's in a top 500 list, by the way. We started off with DGX1 based on Pascal, and it was our first Saturn V implementation, and we had 125 of these DGX1s. We, in 2016, with that old cluster, went to rank 28 of the top 500 list. We were on rank 28 of the fastest supercomputers of the world with 125 nodes. Okay, large nodes, of course, yes. But the most important thing was, on the green 500 list, we went up to rank 1. We were the most energy efficient supercomputer of the world, from 0 to rank 1 within 4 months. We had that implemented within 4 months. So it was the most energy efficient one at that time. It isn't now anymore, because Pascal is not the most energy efficient GPU anymore, Volta is. So at the moment, we have a lot of Volta-based supercomputers up on the top ranks of the green 500. We then actually upgraded. We upgraded a little bit from Pascal to Volta. And we upgraded the number of nodes. We went from 125 nodes to 660 nodes. So what we now have is 660 DGX1 server nodes. In the meantime, it's over 1,000. We now have over 1,000 nodes in our own cluster. What are we doing with this cluster? We're sharing it with some of our customers. So we are part of the Cancer Moonshot program, cancer research, getting to the next, leaping to the next level in terms of fighting against cancer. So a lot of the research institutions have remote access to this installation. We're training our own BB-8 autonomous driving car with this, of course. And as I said before, it's not only the physical car, it's also the virtual implementation of the car in a virtual world. We're training that on this vast, huge installation. And maybe also very interesting, upcoming GPUs will be designed by trained neural nets, aiding our engineers, because we were able to train neural nets to distinguish between good and bad GPU designs. We didn't only have good GPU designs at NVIDIA. We also had some bad ones, which never made it to market, of course. Yeah. So if you train a network to be able to distinguish a good versus a bad design, this is the perfect companion for our engineers if they're developing something. They can have the direct feedback from this trained network, which is advising him, that's a good way to do it, or better do it this way. So the GPUs of the future will be designed by our GPUs. Skynet is almost there, yes. Okay, the topology of the DGX1. I was talking about the individual links we had. If we see the representation of the internals of a DGX1, we see the 8 GPUs we have here. And this is the way they are interconnected with NVLink. So we see connections where we are using 2 NVLinks. We see connections where we are only using 1 NVLink. And we see connections where we have cross connections, but only using 1 NVLink. And we have other ones which cannot communicate directly. For example, this GPU cannot communicate with this one directly. It has to go one hop over the other one. So this was the limiting factor of the DGX1. The limiting factor was not everyone can communicate with any other GPU, and we have differences in bandwidth. And when we have the most bandwidth, it's at maximum 2 links we're using. For example, here. These 2 can communicate via two NVLinks, so we would have the 50 gigabyte per second between these GPUs and only 25 gigabyte between these. So going from 8 to 16 GPUs, we had to think about something else. And as I said before, this is what we then did. We took these Volta GPUs, we took 16 of them, and each of these individual 6 NVLinks connections, in total 300 gigabyte per second, were then fed into this non-blocking switched architecture consisting of the individual of 12 NV switch chips. And this is a non-blocking factor way of connecting every GPU with every GPU and having these 300 gigabyte per second at full bandwidth between any 2 GPUs and having 8 of these communications at the same time running without degrading. If you take these 16 GPUs and everyone can access the memory of any other GPU, it is basically one large GPU. And this is the world's largest GPU. And if you take a look at what it consists of, we're talking about 0.5 terabyte of combined video memory of the GPUs, 32 gigabyte per GPU, 16 of them, gives you 0.5 terabyte. Think of the size of the neural nets you can train within such a node, 0.5 terabyte. And if 0.5 terabyte is not sufficient, we have a unified memory architecture which allows you to use the main memory of the host system in addition. The DGX2 has a host memory a host system which has 1.5 terabyte of additional memory. So you could actually define a matrix which exceeds the 0.5 terabyte of HBM2's memory within it. It's not going to reside within the memory alone. It's going to reside partially within the memory of the host system. You could define a huge matrix which needs 2 terabyte. You could define it, and the system will not crash because we have a page migration engine in hardware within these GPUs, which at runtime will transfer that memory page needed. If it's not within the local memory, it will be transferred by the page migration unit. In former times, you would have to do a CUDA mem copy or whatever. This is not needed anymore. You could program without any CUDA memory copying anymore, and it will not crash. In former times, you would get that blue screen or whatever. This doesn't happen anymore because we have hardware features of a page migration engine which at runtime will transfer that memory page where it's needed and back again. And so this is all solved. We're talking about, as I said, 0.5 terabyte of unified video memory. So it's basically a GPU with 0.5 terabyte of memory, consisting of almost 82,000 CUDA cores within a single instance. And it gives you a performance of 2 petaflops, 2,000 teraflops, 2 petaflops coming from the TensorCourse. So in terms of deep learning performance, it's 2 petaflops of performance within a single node. As I said, every GPU has a full 300 gigabyte per second performance to the other GPU. Just to give you an idea of how much internal bandwidth we have. If we had this internal bandwidth, if we had that bandwidth from our PC to the internet, and we would download all high-definition quality films on Netflix, all of them, not a single film, all of those films available on Netflix in high-definition quality, if we had that bandwidth into the internet, we'll be able to download all that within 45 seconds. If we had that internal bandwidth. That's just to give you an impression of how much internal bandwidth we are talking about. There is no system in the world which has such a high internal bandwidth. This is actually what it consists of. As I said before, it's 10 rack units. It needs 10 kilowatts of power, of course, and weighs about 180 kilo. I think I'm almost at the end, right? Okay. Okay, then I'll come to the last slide. The most important slide. This one. Okay. Did everyone remember my personal promo code? No? Okay, then it's NV for NVIDIA, R for my first name, Hische for my last name. So, if you use this promo code and you register for our event next week, it starts on the 9th and goes up to the 11th. It's a conference which we have over 220 presentations in various fields of AI. It's over 21 autonomous driving vehicles we're having there. All the major car manufacturers will be there. Porsche will be there, Audi will be there, Mercedes will be there, BMW will be there. We're going to have self-driving real trucks there, everything. This is the largest GPU technology conference event in Europe. If you want to come there, come. We have special rebates for academic. Academic students or researchers of institutes received 50% rebate on the normal pricing. And using my personal promo code, you'll receive an additional 25%. To give you an idea, if you take a one-day conference ticket for a student with my promo code, it will cost you about 76 euros, something like that, admission. And we are offering a lot. We have top-notch speakers there. As I said, over 220 presentations. I am within the steering board of the AI speaker slots. I'll be chairing one of the sessions too. Jürgen Schmidhuber will be there. A lot of top-notch AI scientists will be there. You'll be able to interact with industry and academic on all levels. If you can make it, be happy to see you there. And this just search for GTC or GTC Europe, or just take this link, and that's where you can register. Don't forget to use my code. It'll give you part of your money back again. Thank you very much.